All right, welcome back everyone to our Quantum Matter seminar series. My name is Adrian Fagin, I'm your host. Before we start with our program today, I'd like to remind everyone that we want to use these means to somehow democratize science and make it, make the latest research available to everyone. And that's why in our website we have an item on the menu where you can post your suggestions. And I welcome you to suggest possible speakers. And we want to enrich this series with a variety of themes. As you've seen, we have an outstanding group of speakers planned for the future. All right, so having said that, as usual, you're going to be muted until the end of the presentation. When the time comes and the speaker concludes, I'm going to let everyone to interact directly with the speaker. You can raise your hand through Zoom and talk to us, or you can post questions directly on the chat window. And I'm going to read the question to the speaker for you. All right, having said that, we want to keep introductions brief. So today it's my great pleasure to have Greg Fiete from Northeastern University, who's going to talk about non-equilibrium physics in flat band systems. Please, Greg, go ahead.
All right, thanks very much, Adrian. Thank you all for joining. I know that there's a proliferation of Zoom talks these days in the summer as we kind of move into our normal conference schedule. So thank you all for being here. Unfortunately, I can't see all of you, but I know that it's quite nice when I'm watching a Zoom talk to see my colleagues who I would ordinarily be meeting in person. It's at least nice to see their faces. And I look forward to a return when I can also meet new people face to face. So for today's talk, I'm going to be discussing some work that we've done on the non-equilibrium control of moire lattice band structures and magnetism via phonons. So this is kind of a two-part talk, and kind of the themes that we're going to be looking at. Let's see, can I advance? Let's see, my screen's not advancing. Oh, there we go. Okay. Right. So an outline is the following. I'm first going to give a review of motivating experiments. So these are going to be primarily equilibrium experiments. So a theme that we're going to pursue in this talk is looking for layered materials, typically van der Waals type coupling between the layers. And these materials under equilibrium conditions are rather sensitive to things that can influence the weak interlayer coupling. So it might be pressure, it might be electric or magnetic fields. And so we want to ask the question of how much can we create similar changes by the knob of laser. So essentially we want to think about exciting or pumping these materials with the right choice of laser to induce some of the changes that might be achieved under equilibrium conditions in these weakly coupled systems, but also ask the question of whether there's any new phenomena that might be achievable with laser modulation of the electronic properties that you can't get in equilibrium. So the two parts of the talk are going to focus really on two basic material classes. So one of them is graphene. We're going to discuss some results for twisted bilayer and double bilayer graphene around the magic angle, which is, of course, what a lot of people are interested in these days. So we're going to look at those sort of systems out of equilibrium from the theoretical point of view. And then the second part of the talk, we'll look at bilayer chromium triiodide, which has interesting magnetic structure, which is rather different from a single layer or the bulk, and ask if we can modulate that magnetic structure via light. So part one, we're going to look at the laser control of the band structure around the magic angle in twisted bilayer and double bilayer graphene. And then in part two, we're going to look at laser control of the interlayer magnetic exchange via selective excitation of phonons. So both part 1 and part 2 are considering laser illumination of a material, but in part 1, we're thinking of the direct coupling of the light to the electronic degrees of freedom and how that might modulate the band structure. Whereas in part 2, we're imagining the light is lower frequency, targeting phonons in the material. And those phonons can create structural distortions, which then will influence the basic exchange interactions between the layers and can influence the magnetic properties. So before we hit the non-equilibrium regime, I just want to remind everyone of some of the important results in equilibrium. So of course, this well-known paper from 9 years ago looked at the theoretical expectations for the band structure of twisted bilayer graphene around a magic angle, which is about a 1.1 degree twist between 2 layers of graphene. And a couple years ago, there were experiments that realized a material that had twist angles that were very proximate to this. So this is one of the early papers. It's very well known. And what I want to highlight here is just the sort of phenomenon that one sees in the equilibrium situation. So the horizontal axis is carrier density, which could be modulated, say, by a gate voltage. There's temperature. And what one explores by sweeping the temperature and the carrier density is an interesting phase diagram, which has some features that are reminiscent of high temperature superconductors. So there are superconducting regions, superconducting dome, above which there's some kind of a metallic phase. There are Mott insulators that are present. And depending on the twist angle, this is a twist angle of 1.16 degrees. This is a twist angle of 1.05 degrees, kind of on either side of the magic angle of 1.1 that was theoretically predicted. One sees some similar phenomenology, but there's some slight changes of the details of the phase diagram. So here there's an intervening Mott phase over a range of carrier density, whereas here it looks like there's a coalescing of the 2 superconducting lobes. So in an actual experiment, it's difficult to control accurately the twist angle. So it's desirable to have some methods that would allow you to tune the twist angle effectively if the material that you fabricated doesn't quite have the optimal one. And so one route to that is shown over here on the left. There's a device you can essentially put the material in some kind of an environment. Here there's some oil, and you press down on it and create kind of a hydrostatic pressure, which compresses the material. This has the effect of changing the interlayer coupling, which then influences the band structure. So in the theory of the twisted bilayer graphene, the interlayer coupling between the 2 graphene sheets is very important for giving the band structure. And so if you can compress it, then that gives you some degree of tunability of the band structure, can kind of move you a little closer to the magic angle potentially, if you're not as close as you would like to be. And I guess I should emphasize, for those who aren't familiar with this, the magic angle corresponds to the angle where the band around the Fermi energy is very, very flat. So flat bands are of interest for interaction-driven phenomena. So the curvature of a band, I'll remind you, is related to the kinetic energy in the system. So the flatter you make that band, the more the kinetic energy is quenched and reduced as an important energy scale. And this band flattening has very little effect on the electron-electron interactions. So you can end up in a situation where you can change the relative strength of kinetic and potential energy. So graphene on its own has potential energy, which is typically more important, kinetic energy, which is more important than the potential energy. But as the bands get flattened in this magic angle twisted bilayer graphene, then there's a transition, potential energy staying more or less the same, but the kinetic energy getting weaker and weaker. And you can enter a regime, which are the Mott phases in the phase diagrams over here, where the potential energy is dominating the kinetic energy. And that gives rise to new physics and potentially various forms of exotic superconductivity. So the question that we're asking in this talk from the point of view of theory is, can we create a similar response? Can we create similar band structure changes with a laser drive, similar to what we can do with pressure, but could we achieve even greater flexibility? So with pressure, we can only decrease the effective distance between the two layers. With light, could we also increase the distance between the two bilayers? So we have potential to both increase and decrease the effective rotation angle. And then more recently, there's been some growing interest in twisted double bilayer graphene. So shown on the left is a phase diagram from the paper that's cited down here, fairly recent, from I think just a couple of months ago. And there's some similar phenomenology here. The color coding is resistance, just a longitudinal resistance. So red is a larger resistance, blue is a smaller resistance, and there's some correlated state here, this CS, which is something which you might think is analogous to the Mott insulator that was showed on the previous transparency for twisted bilayer graphene. But the blue regions here don't have a resistance, which drops down as nicely to 0. So it looks like you're close to superconducting regimes, but it doesn't quite reach there yet. So my point in showing this transparency is just to say that it appears that the double bilayer graphene, which is essentially a 4-layer system, appears to show some similar phenomenology to the twisted bilayer graphene. So this is another material that we might consider looking at. And in fact, we look a little bit at that from the point of view of laser-driven electronic band structures. And we find some interesting features that are present in the double bilayer graphene that are not present in the bilayer graphene itself. And then the last part of the talk, kind of to put everything all together at once, will be on chromium triiodide. So here we're interested not so much in the modulation of the band structure going from an insulator to a conductor or a superconductor, but we're interested in changing the magnetism in the material. So chromium triiodide is a layered structure with van der Waals coupling between the layers. A single layer is ferromagnetic within the plane. A bilayer has ferromagnetic coupling within a plane, but anti-ferromagnetic coupling between the planes. So that's what's shown here. And if you go to the bulk limit, 3 layers or larger, then you have both the ferromagnetic coupling within the plane, but also between the planes. So the bilayer is rather special. It's suggesting that because there's a difference between a bilayer and a trilayer system, there must be a very weak interlayer magnetic exchange coupling, and that might be tunable with some sort of external parameters. So what's shown here is exactly that. So on the left figure, this is a magnetic field tuned transition. So for very large negative fields, the bilayer system, so this represents an upper layer and a lower layer, there's the ferromagnetic order within the layers, but for large magnetic fields, you just fully polarize the system, spin down for negative fields, and spin up for positive fields. However, for very weak fields or zero field, there is the anti-ferromagnetic coupling in the bilayer, which is preserved. So a magnetic field of order less than a Tesla can change the overall moment from 0 here to a finite net moment. So this is an external magnetic field applied perpendicular to the planes. One can achieve a similar sort of effect with a gate voltage. If you just gate the bilayer system, then you can achieve a regime for a sufficiently large voltage where you can drive the system into a ferromagnetic regime. So applying an electric field and breaking the inversion symmetry of the system can also drive you into a ferromagnetic phase from the preferred anti-ferromagnetic phase at 0 voltage. And then finally, over here on the right-hand side is the result of applying pressure to the system. So we also saw that pressure could change things for the twisted bilayer graphene. That's true here. So at 0 pressure, 0 gigapascals, and 0 magnetic field, the system has this anti-ferromagnetic orientation between the 2 layers, again, ferromagnetic within the layers, And as you increase the pressure, then the system makes a transition into a ferromagnetic state, which switches from an up ferromagnetic state to a down ferromagnetic state on either side of the zero field. So again, our question is, can we achieve these sort of effects out of equilibrium with a laser driving the system? So you might wonder, why are we interested in achieving the same thing with a laser? Well, one reason is that it can be done very quickly. Lasers can be turned off very rapidly, and it can be reversibly done. So rapid and reversible. Some of these sort of measurements, applying these magnetic fields, the gate voltage and the pressure, the time scales for which one can do that is very long compared to the turning off and on of a laser. So we could achieve reversible transitions. These are also reversible largely, but we also gain speed. Okay, so now transitioning into non-equilibrium systems, I want to remind everyone on the call that there's some interesting examples that exist out there for the sort of things that one can achieve independent of the two material classes that I'm discussing today. So, there are so-called Floquet states, which I'll cover in a moment in more detail. But if you have a periodic Hamiltonian, so that the Hamiltonian after some amount of time returns to itself, and this is what you have, for example, if you have a constant laser, continuous wave laser acting on a system, then the Hamiltonian of that system is time periodic by virtue of the electric field of the light being time periodic. So in typical experiments, such as the one done in the Gedik group at MIT, there's a pulse of light which comes through, and the pulse of light has some electric field oscillations that exist over the envelope of the pulse. And what one sees is during the period of time when the pulse is oscillating, you're the center of the pulse, you generate multiple copies of the bare electronic states, which in this case are the Dirac cones, the surface states of the topological insulator bismuth selenide. So this is the sort of thing that is observed in this experiment. So there's a creation of copies of the electronic states, which are essentially a kind of photon-dressed electronic band structure. And so this experiment is done by shining light in, ejecting electrons with the light, and capturing these electrons, measuring their energy and momentum. And so you can reconstruct the electronic band structure. So another sort of phenomena that occurs, that's a non-equilibrium phenomena that exists only when the light is illuminating the material. Just by way of contrast, I want to give another sort of example where a single pulse of light can induce a long-lived change in a material. So after the pulse has left or been dissipated in the material properties are changed. The example that I showed earlier with the Floquet states was focused on electronic band structure. And so here's an example which also contrasts in the sort of changes which one can obtain, and this is a magnetic change. So this material, this lanthanum calcium manganese oxide, has in its non-illuminated state, or its pre-illuminated state, basically an antiferromagnetic order. It's electrically insulating. So here's the phase diagram. So in zero magnetic field, system is an antiferromagnetic insulator. But if you hit this with the pulse of light that is above a critical fluence, there's a critical amount of energy in that pulse, then you can induce a change in the material where it goes from electrically insulating, the green curve here, down to electrically conducting. Moreover, you induce a ferromagnetic order. So you change the material from an antiferromagnetic insulator into a ferromagnetic material, and this metallic ferromagnet can live in this metastable state for weeks at a time. So it's almost as if you've got a new material with just a single pulse of light. So this is a sort of phenomenology that one can find in highly correlated states. This sort of thing may be relevant also to like the twisted bilayer graphene or even chromium triiodide, because correlation effects can be a dominant factor there. Okay, so once we're interested in modulating and changing the properties of a material with a laser, once it quickly realizes that there are a lot of parameters that can be controlled with a laser. So there are a lot of knobs to tune, in other words. So the polarization of the laser, for example, can be changed. One could work with linearly polarized light, which preserve time reversal symmetry, or circularly polarized light, which would break time reversal symmetry. One can adjust the frequency of the laser. So the frequency of the light obviously is very important for selectively coupling to certain degrees of freedom. If you want to couple to electrons, you might choose light that is in the visible range, kind of EV range, or if you want to target phonons, you might be in the IR range. So your frequency is a knob that you can use to selectively tune excitations in a material. And of course, these excitations are going to be coupled. If you excite the electrons, eventually their energy can be released into phonons. And if you excite phonons, then that energy can also be transferred into the electronic degrees of freedom. So there's a coupling between them, but there's a question of time scale. So what is excited first? And then how does that energy flow through the various degrees of freedom in a material? So lasers give you a way to control that in real time. So you can also vary the intensity of a laser, often called the fluence. It's just the time integrated flux of a laser. So in the example of the magnetic material I just described, you need a critical fluence in order to induce this metallic ferromagnetic state. If the intensity of the pulse isn't large enough, that change will not be induced. And then once you've achieved that critical fluence, then anything above that seems to give kind of a similar response. And so that's probably related to some kind of energetic landscape. You probably need to get over some kind of energetic barrier in some high dimensional space. You can also change the angle of incidence of the light relative to the material orientation. So there's going to be selection rules that are involved, analogous to what one has for an atom. Of course, an atom has a spherical symmetry if there's no magnetic field present. But once you have a magnetic field on an atom, then the electric field orientation relative to that is important. So there's analogs, of course, in a material. You might get a larger or smaller response, or there might be certain crystallographic orientations relative to the electric field of the light that you don't excite certain modes, whereas for other material orientations relative to the electric field of the light, you may. And then there's some other, kind of more exotic directions, which I think are topics that people are just starting to think a bit more about in the context of condensed matter physics, and that's pulse shaping. So this, pulse of light, if it is shaped, it's chirped or modulated in some sort of way, then that might produce some interesting responses in a material. Or maybe the time dependence of the response can be modulated in an interesting way in terms of energy transference between the degrees of freedom and the material. So I think that people are just starting to think a little bit about that in the context of condensed matter physics, although in quantum chemistry, that's been a tool that's been used for some time in order to influence chemical reactions in real time. And then the last thing I put here is that one needn't restrict him or herself to one laser. You can have two lasers that illuminate a material at very different frequencies, very different intensities. So you can produce a response on top of a response. You might have one laser which establishes a kind of modulation, say in the carrier density spatially in a material, and then you shine another laser that looks at the response of this grating that's been created in a material. So there are many things that one has to play with here. And I think we're kind of just scratching the surface of the kind of control that can be obtained by illumination of quantum materials with lasers. So that's kind of the direction that we're heading, generally in these projects that I'm describing. Okay, so a few generalities on Floquet systems before we kind of launch into the main part of the theory results. So, Floquet systems, as we mentioned earlier, are periodic in time. So here, capital T is the period, H is the Hamiltonian, little t here is the time. So the Hamiltonian comes back to itself after some period T. And this is a sort of situation that, you know, anyone who's had a solid state course is very familiar with, because this is what happens in a crystal just in real space. So there's a discrete translational symmetry in a crystal in real space. And we learn in a first solid state course that the consequence of that translational, the discrete translational invariance, is that momentum conservation is only retained up to some arbitrary amounts, these reciprocal lattice vectors. So what one gets is a reduced region of momentum space that contains all the information of the system. So that's called the Brouillon zone. So here's a one-dimensional system shown. So if there's a larger momentum, it just gets folded back and it contains the same information that's in this regime. So instead of having all momentum that are important, we just have a restricted range of momentum. And so the same thing happens if we have a periodicity in time rather than in space. So we just have the conjugate variable to time, which is energy, in the same way we have the conjugate variable to space, which is momentum, that essentially becomes periodic. So, you know, shown here, there is a periodicity in frequency space, so that the energetic states just get replicated every so much in energy, which is related to the frequency of the drive. And once you have this kind of replication, then there is no longer kind of an absolute sense of high and low energy. So the states just go up arbitrarily high, the states go down arbitrarily low. And this creates a little bit of a confusion of, you know, which states are lower in energy than another. And so just to kind of highlight this issue here, the two black curves here might be a particular choice of this two-band model. We might say band 1 is lower in energy and band 2 is higher. And then we could replicate that up to this gray level, replicate it down to the two gray levels here, and that would fill out our energetic space just fine. Or we could have made another choice. So we could have chosen band 2 to be the lower energy and then band 1 to be at higher energy, and that would replicate. So we lose this notion of high and low energy. In order to kind of, you know, break this degeneracy, we need to know some information about how the laser was turned on, or we need to know how these electronic states are coupled to external degrees of freedom, you know, like phonons or magnons or some kind of a bath, which would provide a selective population of these states. So if we're thinking about band structure, which we are for the moment, one would like to calculate the energy momentum relations under this periodic drive. And so the standard procedure is to essentially enlarge the Hamiltonian. So you have an undriven Hamiltonian, say H0, and this undriven Hamiltonian is going to have a band structure, and the bands are going to be coupled to replicas of them that are separated in energy by an amount which is 2 pi over the drive frequency, or in other words, essentially the energy contained in that frequency of the drive, you know, h bar omega. And so that would be like a one photon process, you know, coupling up or coupling down. So those are the off diagonal terms delta. And then if you go further off the diagonal, you couple terms with 2 photons, 3 photons, et cetera. And in principle, this is an infinite dimensional matrix. And in practice, you truncate it to a certain number of copies, and typically something of order 10 can give you accurate descriptions of the physics. So this is the sort of structure that one gets. There are energy momentum relations that in the absence of 1, 2, 3, or 4 photon couplings, they're bands that cross. But then once you include the photons that couple the different copies, then gaps can open up between the different bands, and you can end up with band structure that in equilibrium would look like an insulator if you had placed the Fermi level in certain positions. So you can ask the question of whether these insulating-like band structures have topological invariance associated with them. And one of the interesting results that's been discovered and reported in the literature is that, yes, you can have topological properties associated with these bands, and then you have potentially topological edge modes that are associated with these band structure changes. But the relationship between the Chern numbers in the bulk, for example, and the boundary modes is much more complicated in these Floquet systems. You lose some of the nice one-to-one correspondence that exists between, say, Chern numbers in an equilibrium system and the number of boundary modes. So, Chern number n guarantees a minimal number of n boundary modes in an equilibrium system, but in a non-equilibrium Floquet system, you can have 0 Chern number and finite boundary modes, or you can have finite Chern number but no boundary modes. So the situation is more complex, and one needs to look at generalized invariance. Okay, so how do we mathematically handle these Floquet systems? This is a standard tool, something called the Magnus expansion, which is used for large frequency drives, which essentially means drives of the system where the frequency is large compared to any other energy scale, such as the bandwidth or interaction energy in the problem. So it's an expansion in powers of the inverse drive frequency omega here. And the terms that are appearing in these commutators are essentially Fourier components of the Hamiltonian. So for n equals to 0, there's just the time averaged Hamiltonian, that's H0 here. And then for n equals to plus or minus 1, those correspond to the first Fourier mode of these Hamiltonians. So if you're only interested in large frequency properties, this is a powerful tool. But in many cases, it's the low frequency behavior that is of interest. And one reason is, as a theorist approaching this problem of light matter interaction, one is typically biased to thinking of coherent responses. Oh, there's a laser on a material, we know how it's going to couple. We're going to get a coherent quantum response. But in practice, lasers have a lot of classical heating effects on materials. And if the photon energies are larger, so you're in this large frequency limit, you're putting a lot of energy into the system. And so that's going to lead to a lot of heating. So from the point of view of trying to produce coherent responses of a material, there's definitely interest in looking at lower frequency drives because the photon energies are just going to be lower. So when you go to lower photon energies, though, these Floquet copies, which are shifted by an amount of the drive frequency, start to come closer and closer together, and you get many, many overlaps of these bands. And that corresponds to many possible mixings with many photon processes mixing these things together. And so that presents a challenge to this Magnus expansion. So one needs to address this low frequency regime. So here I'm going to transition into some of the results from our group. So Michael Vogel and Martin Rodriguez Vega are responsible for this work, and essentially all the work that I'm going to talk about in the context of graphene. So here is kind of a setup to bilayer graphene. So the question is, how can we address this low frequency regime? So in general, it's very difficult, but if the drive is weak, so the intensity of the laser is very weak, then the multi-photon processes will be much less important. So what one can do is analyze the low frequency regime where there are many resonances in the limit of a few photon processes. So essentially that's what's done in this work here. And the logic is carried over from what I described at the beginning when I introduced the Floquet states. So in real space, we end up with a zone folding scheme where larger momenta get folded into a single Bruron zone. We could imagine doing the same kind of zone folding scheme, but now in frequency space. And so that's what occurs here. And then we have kind of a 0th order band structure where we've just folded these things in on one another in the same way as we kind of have like an empty lattice approximation for the momentum case. And then one can look at the properties of the crossing points and ask whether there are gaps that are open, and if so, how are they open, et cetera. In the same way that one looks at kind of a perturbative effect of a weak periodic potential, to open up gaps at the zone boundary. So a key ingredient here is a self-consistency condition on this Hamiltonian. So that self-consistency condition is important to get a very accurate band structure, and that's what's shown here, as well as accurate wave functions. So you can see that the two curves here are nearly indistinguishable by eye. So one is a direct evaluation of the full Floquet Hamiltonian, including many copies. And the other is, which lies right on top of it, is the approximation that I just showed, which is down here, this kind of weak coupling, a low frequency approximation. So you can see they lie right on top of one another. One can test the accuracy of the wave functions by computing a Chern number. So this is done for graphene, by the way, with circularly polarized light. That breaks time reversal symmetry. So there can be a Chern number. And what's shown here is the Berry curvature in momentum space. And here is the Chern number as a function of the number of points in momentum space. Again, there's the black curve and the red curve, which lie on top of one another. They are the evaluation of the Chern number using this effective theory compared with an exact diagonalization of the full Floquet Hamiltonian, but truncated with enough copies. So this is a highly accurate method for these low frequency weak drives. So now we want to turn to twisted bilayer graphene. So we're going to imagine that we irradiate this twisted bilayer graphene with a laser. So it's a normal incidence. And this twisted bilayer graphene leads to a moire pattern, which has a very large spatial size in the unit cell, which offers a number of advantages from the point of view of illumination, it turns out. But it has a consequence in reciprocal space. If we're very large in momentum space, then we get shrunk down in momentum space because it's a conjugate variable. So the Brouillon zone kind of shrinks down. And the Hamiltonian looks something like this. So there are pieces, a little h. Little h describes the band structure of a single layer. And there's an angle theta for which these layers are rotated with respect to each other. So one is rotated minus theta over 2. Another is rotated theta over 2 for a total angle of rotation of theta. And then the terms here t describe the interlayer coupling between these two. So that's very important, that interlayer coupling, which is really parameterized by a W0 and a W1 here, which is, turns out you can relate that to the kind of stacking order. It produces this red band here, which is very, very flat. So this is the band structure of this Hamiltonian for parameters that are very close to the magic angle. So you can see this is a very flat band. So this is in equilibrium. So we want to ask about non-equilibrium situation. So light is going to couple to the motion of the electrons through the vector potential. So that's a P dot A type of term in like first quantized form, or J dot A in I guess a more many-body type of language where J is the current. So if the electrons move in a direction along which the dot product with the vector potential is finite, then the phases of the hopping will be changed by the presence of the vector potential from the light. So this is coming from a laser. So this has the effect of shifting the momentum. So what was kx before is now modulated by the frequency of the light. This is the amplitude of the vector potential, and the y component is as well. So we've assumed here a circularly polarized light. That's the sine and the cosine components. Now, when the light is normal incident on the material, there's no component of the vector potential along the direction of the light. So all the components of the light are in the plane of the bilayer graphene. So that point is important. We'll come back to that later. But before we get there, let me just describe some of the results that occur here. So here is now the time-dependent Hamiltonian, where it's the same thing that I showed earlier, only the momenta are now time periodic coming from the laser drive. And then in order to apply the Floquet formalism, we need to look at the Fourier components of the Hamiltonian. And so the Fourier components are coming from little h, which is built out of little f's, which describe the the intra-layer hopping. And so we get these terms here. And then the out-of-plane coupling only picks up a zero frequency component because that doesn't have any time dependence. So the result of this work is one can derive an effective Hamiltonian in the weak drive and in fact arbitrary frequency limit. So I kind of motivated things by talking about the low frequency limit, but we didn't restrict ourselves to that. That was just highlighted because that's kind of a technically challenging limit. The approximation's key aspect was the weak drive part to it. So one can show that one ends up with an effective Hamiltonian, effective Floquet Hamiltonian with this drive frequency omega that has these terms here. And so, depending on how you choose the drive, going back to the transparency I mentioned, there are all these parameters that one can change in the laser, depending on how those are selected. One can look at the various terms here in this column, which are the same terms that are appearing here in the Hamiltonian, whether they are present with a check mark. So this is like a C2 rotation followed by time reversal operation, C3 rotation. This is a mirror reflection about the y-axis. Whether it's present or absent with the check if it's present, absent with an X. And one can essentially choose your drive to produce certain terms in this Hamiltonian, which might give you responses in the band structure. So the sort of results that one finds here are the ones shown in red. So the gray dashed lines are the equilibrium band structures, and then the reds are the non-equilibrium ones where certain parameters are selected. So here U is not equal to 0. There's a kind of tilting, if you will. So one crossing point is shifted down and another crossing point is shifted up. So you have a kind of selectivity on these two. One can also induce gaps in the system. It's a little hard to see here. They could be asymmetric gaps. One can change the dispersions, change the velocities. One can shift things, upwards or downwards. So light allows you to modulate the band structure in all of these ways. And there's a procedure which is outlined here for how you actually calculate these coefficients depending on the properties of the drive. So kind of as an aside, I'll just mention this work, which provides a powerful method to calculate these kind of coupling constants, which, Michael, who's also a co-author on the graphene stuff, worked on last year. So if you're interested in effective ways to calculate things, I want to draw your attention to this. The one feature that I'll highlight is that this kind of approach, this so-called flow equation approach, allows one to access lower frequency. So this is the error, this is the drive frequency. And if you compare with a Magnus expansion, which I emphasized was valid at high frequencies, with this flow equation approach, which I'm kind of glossing over the details here, but it allows you to reach into much lower frequency regimes. And so this kind of connects with some of the studies. So I'm highlighting this as essentially just a tool that's available for theorists who want to reach into the lower frequency kind of multi-resonant regimes. Okay, so now I'm going to present another work on the magic angle graphene, twisted bilayer, but I want to come back to the issue of the vector potential and how it couples to the bilayer. So I mentioned before, for a normally incident light, the vector potential components are going to be in the plane. It won't have a longitudinal component. And the longitudinal component is what we would like, because then we can modulate the interlayer coupling. So what Michael and Martin realized is that a waveguide can help you do that. So a waveguide can produce a longitudinal component to the vector potential, which is shown here. And then that vector potential, if you place this twisted bilayer graphene right at the exit of a waveguide, and you want to have a sample which is small enough compared to the dimensions of the waveguides that you have approximately uniform vector potential over the region of the sample where you're doing your measurement, that makes the interpretation a little bit easier. And so what one finds is that it's now these interlayer terms which are modulated by the vector potential. Okay, so it's kind of contrasting with the other. It's the other situation. And what's shown here is a zoom in of the band structure. So the gray is the static case. It's close to the magic angle. And the driven situation here shows, this is a large frequency drive, shows that you can get an increase in the velocity. So you can tune your angle in such a way, in this case, that the velocities would be increasing. So if your angle were not quite optimal, a little too small, you could increase your angle, say, and get a larger velocity. Now, it turns out that if one looks at a regime of slightly lower frequencies, but a regime where the frequencies are large compared to the bandwidth of these flat bands, which is capital W here, but still small compared to the gap between the flat bands and other bands, which is delta here. And one works in this kind of intermediate frequency regime where the frequency is large compared to W, but small compared to delta. Then one can achieve the opposite effect of flattening the bands, so decreasing that Fermi velocity. So I just want to draw your attention to the green dots, which are overlying the red dots here. So again, the gray is the undriven system, and the green overlaid with the red. These are two calculations that are looking at a different size of the Hilbert space to get convergence. They lie on top of one another here, so there's good convergence. So we can also decrease the Fermi velocity and flatten them. So this technique of putting this twisted bilayer graphene in front of a waveguide essentially gives us full control over the dispersion. So we can create a situation where we effectively either increase or decrease the magic angle, and we can kind of tune it in situ. So this might be highly desirable for certain applications. And in the last topic I'll cover here with the graphene case, we'll look at the twisted double bilayer graphene. So now we've got 4 layers, and one can achieve also a situation where the bands near the Fermi energy are very flat. There's similar sort of phenomenology with the boron zone, et cetera, and the large moire lattice. And the feature that I want to highlight with the twisted double bilayer graphene is that if one applies an electric field perpendicular, one can have a lot of valley control over the gaps in the system with pumping with light. So here, this is the amplitude of the light for some particular frequency, and one sees that the different K and K prime valleys respond rather differently. So one gap will grow, another gap will shrink and even vanish, or they can follow each other in a more complex way, as shown in the figures here. So depending on how one chooses the parameters of the system with an electric field, without an electric field, like a positive or a negative direction electric field, one can achieve a lot of valley selective control of the electronic band structure. Okay, so now for the last part of the talk, I want to transition to magnetism and how it can be controlled by light. So this is a repeat of the transparency I had earlier. I just want to remind everyone that bilayer chromium triiodide has an antiferromagnetic orientation of the spins between the 2 layers, and within the layers there's a ferromagnetic order, and that can be modulated with magnetic field, gate voltage, or pressure. So we want to address this from the point of view of driving the material. So for the bilayer graphene, I was imagining that the coupling of the light was directly to the electronic degrees of freedom. That's how it was put into the Hamiltonian, because it modified the electron hopping parameter through a sort of minimal coupling scheme. In this situation, we're trying to modulate the magnetic properties by targeting the phonons in the system. So this work is rather involved. It has a combination of elements of group theory, first principles calculation in order to put all these pieces together. So let me try to walk you through it. So group theory, one can apply to chromium triiodide in order to use symmetry to determine what are the various modes of bilayer chromium triiodide that would potentially modulate the interlayer magnetic exchange. So that's the thing which is weak, because we can change the interlayer preferred magnetic order, as we've seen with an external magnetic field, with an external electric field, or with pressure. So we want to do it in a different way. So group theory and this symmetry analysis allows us to identify certain vibrational modes of the lattice. Now, the vibrational modes that are relevant are Raman modes. So these are typically not directly excited by a single photon. So we want IR active modes to somehow couple to these Raman modes. So we want to use IR frequency light to selectively excite the phonons. Now, it's a little difficult to see perhaps, but there are some darker dots shown in the upper right corner here. This is, by the way, a result from density functional theory, which has calculated the zero wave vector phonon modes of chromium triiodide. And the modes shown up here, these three modes are IR active. The blue modes down here are Raman active. And those are the ones that are shown in these figures, the little yellow arrow showing the sort of displacements that are present. So we want to somehow couple these IR modes, which are the ones that the light is going to naturally excite at low frequencies, to the modes down here. So using a kind of Landau-Ginzburg type of analysis, we can write an effective potential for these vibrational modes. So essentially the lattice at this point is being treated in a classical sense. There's classical oscillations. So there's the potential is quadratic, and the displacement Q of the IR mode, there's some kind of a frequency of that mode, which is, we're going to select one of these. And then the Raman modes, there are three of them. Those are the three blue ones shown here, and those are the three shown here. Those are going to have their frequencies. And then there's going to be some anharmonic terms. So this is the critical point. So we need to have coupling between the IR and the Raman modes, and they're going to appear via anharmonicities. So here there's a square of the IR mode coupled linearly to a Raman mode. Here's a square of a Raman mode coupled to another one, a square of a different Raman mode coupled to another one, etc. So these coefficients, the deltas, the betas, the gammas, epsilons, and the x's, these can be calculated from first principles. So that's what we did in this project. Our collaborators did that. And then what we find by solving these equations, assuming a particular time dependence of the IR mode, which is essentially following the electric field envelope of the laser pulse, we get a result for the time dependence of the Raman mode. So again, the procedure is the light excites the IR mode, which is coupled through nonlinear terms to the Raman mode, and then we end up with this particular displacement of the Raman mode, and it turns out that this has a shift in it. So essentially there's a kind of transient shift in the crystal structure, which then leads to a modification of the exchange via kind of an interlayer hopping that modulates the magnetism. So that's the goal. So the interlayer magnetic exchange typically has some Heisenberg terms, and it has some other spin orbit coupling terms, which are anisotropic. So what one finds is that if one looks at the time averaged Raman mode that's going to couple to the magnetic degrees of freedom most predominantly, then one sees that this can be negative in sign, or it can be positive in sign. So we can modulate potentially the Baire exchange between these layers. So because there is the Baire exchange And then there is a shift of the exchange energy, which is related to the shifts of the ion positions coming from these Raman excited modes that we've coupled to via the IR active modes, via a nonlinear phononic sort of scenario. So it turns out that the microscopic exchange parameters that are involved, and these can be computed from density functional theory, are rather complex. It's not just the nearest neighbors that are important, but there are a number of neighbors close by. And so what we did is we came up with a kind of effective Hamiltonian. We said, let's imagine that we're kind of averaging over all of these, and we're putting that into some kind of effective exchange parameter. So that's the colored curves here. The blue and the purple are independently averaged in the plot here. And so the critical thing to note is that for different values of the displacement of this Raman mode, there is a sign change in the exchange coupling between the layers. So there is an interlayer sign change of the coupling, which can be achieved to bring the system from an anti-ferromagnetic order all the way to the ferromagnetic order. So this is, in a sense, a kind of dimensional crossover, as the title of the slide says. So we can make the 2D system achieve the magnetism of the 3D system with this sort of selective excitation of this Raman mode via this chain through the IR active mode. Okay, so I'm just about at the end, so I want to thank the collaborators. Martin Rodriguez Vega is a postdoc working in the group. He played an essential role in many of these projects, including coming up with the ideas for them. Really grateful to him. And Michael Vogel is kind of his partner in crime on the graphene projects in particular, and has now moved out of the group. He graduated this year. He's joining a faculty position in Saudi Arabia starting in August. So he's kind of in a layover in Germany right now, where he's from. Zetchen Lin is a graduate student in the group, contributed a lot to the chromium triiodide project I discussed in the end. And then Aritz, Gaurav, Arthur, and Maya helped a lot on the first principles components of the project. So we're really grateful for their contributions, so that the results I presented are actually, the numbers in there are specific to chromium triiodide, and we estimated laser intensities and fluences to see that those sort of interlayer coupling changes were reasonable. Okay, so to summarize, we've studied periodically driven laser illuminated two-dimensional weakly coupled layered systems, and we focused on Floquet band engineering of twisted bilayer and double bilayer graphene near the magic angle, but the approach is applicable to much more general systems. Essentially, any kind of van der Waals type material with weak interlayer coupling, one can apply similar strategies as we have applied here. Just there'll be details of the input Hamiltonian that will be different, but the kind of messages that emerge are applicable to those. And then the last topic, the phonon modulated interlayer exchange coupling in bilayer chromium triiodide, it's the same situation there. So any kind of weakly coupled van der Waals type layered material with magnetic order is a candidate for magnetization modulation via this kind of nonlinear phononics route. So I'll stop there. Thanks very much for your attention. I'm happy to take any questions.
Thank you, Greg, for a very nice talk. We open the session for questions. So if you're in the audience and you want to ask a question, please feel free to raise your hand and I will unmute you. Otherwise, you can post a question on the chat window and I will read it to the speaker.
Okay, I think Bert, your hand is raised.
Yes, thank you. It was a beautiful talk, very clear and very nicely presented. Just a very minor question. Why do you need to use a waveguide to get this perpendicular field? Can you just tilt the sample relative to the electric field and get any angle you want?
I mean, I guess you could do something like that. I mean, here, what we did is isolate the effect, because in this particular scenario, the vector potential, which is dominant, is just this longitudinal component. So I guess this was a way to kind of isolate that. I mean, in principle, you could rotate the sample, but I guess I'm not sure if it would have other influences on the band structure. Like, I don't know what the net effect would be. It might be that you get some help with the longitudinal component, but you might get hurt in the, like, you know, intra-layer components. So, I mean, we didn't look at that in detail. So yeah. So
what I had in mind was something where you have a purely transverse electromagnetic field coming in. Let's say it's polarized with the electric field in the X direction, and it's coming in from the Z direction or something like that. Now I can rotate my sample so that the plane of the sample is perpendicular to the Z direction, to the X direction, and then I just have an electric field that's perpendicular, and that's all there is.
Yeah, so I think it could also be a question of intensity. I think that the waveguide gives you, you know, larger intensity, and that may be a critical factor.
Okay,
as well. Yeah, but yeah, good question. Anybody else?
Hello?
Yes.
Yeah, so sorry, I have one question, but maybe it's stupid. If there is one effective model you presented for twisted, and you show the one flat band, which is very red, could you back?
This
yeah,
right
yes,
here?
Yes, here. There is a very flat band red, which comes from this effective Hamiltonian. But as I understood, this effective should give you totally 4 band. But here you have many bands, more than 4. How did you get this one?
Well, I mean, I think there are 4 bands here.
No, just if you count from the top to, you see there are 1, 2. If this is 4, is okay.
Yeah,
So
I mean, I think it's okay, because I think they're just crossing one another there. I think it is 4 bands. I guess I should check with Martin or Michael if they're on. I don't know if any of them can, if they're on, they can chime in, but I think it is 4.
Sure. So I'm here. I'm Martin.
Okay, yeah.
Okay.
What's the question?
Question is whether there are 4 bands in this figure that's shown right now. Like, if these things that are crossing, that's just a continuation of that band.
I mean, so
why are there more than 4 bands?
Yeah.
So you see, each sheet of graphene should give you 2 bands. If you have the 2 of this sheet, totally you should have 4. But here you have more than 4, as I'm seeing. But maybe I'm wrong.
The Hamiltonian that you see here on the HKX, that's defined in momentum and position combined space. So you have to project that into a suitable basis to plot the band structure, which is what's been done here in figure C. So in principle, you have like an infinite number of bands, and you just use as many as you need for convergence.
It means you can use all those in the first Brillouin zone. Mm-hmm. Okay. Yeah. So another question: all this result which you show for this just twisted bilayer has been found with this fellow approach. I mean the time dependent.
Yeah, I mean so the results that were presented here. Mm-hmm. This is all time dependent study, so it's a periodic drive. All of these results.
The approach you use to find this one is the flow equation you presented in PRX.
So I think that the flow equation can be used for some of these in some limits, but I think that you can achieve some of them outside of that approach as well. I just kind of advertise that as like a general tool to achieve some accurate estimates of these kind of parameters as you go into the low frequency limit.
Mm-hmm. Yeah, okay. So, but specifically, for example, for this sheet of presentation, for these four figure, did you use that approach you presented in PRX for this one or not?
No, I think here it was just exploring the effects of the terms in the Hamiltonian. So we just said, for an A, we just say, let's suppose that U is not equal to 0.
Mm-hmm.
Then what is the effect of a non-zero U on the undriven band structure? And likewise for B. So, there's not a numerical value for U that's highlighted there. It's just non-zero U will create this kind of, opposite shift of the two Dirac crossing points.
Okay.
So I think it's meant to illustrate the features of the band that can be changed by the presence of these parameters when they're non-zero.
Okay. Okay. Thank you.
Yeah. Thank you for the question.
Nancy Sandler, please go ahead. Sorry, can you start again? You were muted, sorry.
Oh, okay. It was a beautiful talk and I really enjoyed it. So thank you very much for giving it, for presenting it. I have one question about the last part of your presentation.
Okay.
It seems that the nonlinear coupling between the RI and the Raman modes is crucial to get this change in the exchange coupling. Is that coupling being nonlinear? Naively, I would have expected to be important for higher fluency. Is it consistent with the weak driving approach that you are taking?
Right. So so I think, let me make sure that I got your question. So you're asking if the nonlinear terms that I have included are sufficient for the sort of laser drive strengths that I would need in order to get a response.
That's right. If the two conditions are consistent or can or if with weak driving you should get enough nonlinear coupling to have the effect on the change in the sign.
Yeah, I think that it would work out. So this was a quantitative study. The phonon frequencies were calculated from first principles. The coefficients of the nonlinear terms shown here, they were calculated from first principles. And then we estimated for, say, electric field strengths in light, what would we need the electric field strength in the light to be to produce a displacement that was sufficiently large to create the sign change in the interlayer exchange coupling. And so those parameters work out with something that is achievable in experiment, as far as we understand.
That's really interesting. That's really interesting. Okay, thank you.
Yeah, thank you for the question.
All right, it seems that we don't have any other questions. So we thank Greg Fiete one more time for a wonderful talk. And we thank the audience for being here with us. We invite you again to join us next week for Andrei Bernevik's talk. You'll get reminders in your email. And have a wonderful rest of the week. Goodbye.
Thanks, everyone.